Thank you. I'm not used to speaking with a microphone, so you'll have to help me with that. Louder? Okay. So I'll try harder. So my name's Gordon Wesley, also known as Flash Gordon. Never heard that before. So I'm an engineer, mechanical engineer with the McDonald Observatory. I've been an engineer there for 25 years. I actually retired back at the end of May. And retirement's great, but I've come back and I'm working part-time to help them hire somebody to replace me. And I enjoy the work. It's nice and fun and really creative. So let me get started. So what we're going to talk about tonight, I don't remember what the billing was, but I'm just going to talk a little bit about designing instruments. There's a lot to it. And over 25 years, I've designed a lot of instruments and a lot of parts for telescopes and supported telescopes when they broke and things like that. So I had a really hard time thinking up what I'd talk about and finding all the slides that would go with it. So I'm going to talk about designing instruments there, the kind of design flow, the considerations, and the steps we go through to design and build an instrument. A little bit about fabrication, assembly, and installation. And then the maintenance of our telescopes. Our telescopes are getting pretty old, most of them. And let's see. So the disclaimers, I'm not an astronomer. Okay, I can find the sun and the moon, most of the dippers. I know Orion when I see it, and I can find Cassiopeia. But that's about it. So don't ask me any astronomy questions, okay? And then finally, I just wanted to give a little blurb about my first career, because some people are interested in that. So this is me 40 years ago or so. I hadn't grown my beard yet, but I've had that mustache, I think, the whole time. My wife of 20 years has never seen me without a beard. So anyway, this is me. This is actually outside of Kansas City. So I worked on cross-country pipelines. These are the lines that are buried in the ground that move the petroleum products and crude oil around the country. My job was primarily, I was a diesel mechanic, and so I ran the engines and the pumps and things that we did the testing with. And so this is a setup. I'm kind of right there. We had a charge pump, and these are turbine-powered pumps, and we would fill the pipe with water, push the product out, and would pressure them up and see what would happen. And frequently, we would split the seams out of some pipe, okay? They're old pipe, and we'd put them up to about 125 or 130% of their operating pressure. So we would test them at those pressures so we wouldn't pour product out on the ground. So that was a seam split. That over there is a corrosion pit that blew out. And I just like to always show this picture. I can tell you about this later, but this is a piece of pipe that actually blew up in the ground and blew out of the ground. So that was a fun career, but I gave up on that and I went back to school to get an engineering degree. And when I graduated, I went to the university, moved over to the astronomy department, been there ever since. So some of the types of instruments we build are photometers. These count photons coming in. They can detect variations of light and the brightness of an object. For example, a planet passing in front of a star. And then we build imagers, and those just take a picture of the star field. They throw filters in front of it and just take pictures of it. And then there are spectrographs. There are a lot of spectrographs out there. We're building some now here in Austin, and they split up the starlight into its component wavelengths. And then they look at the very small shifts in the position of the wavelengths, and they can use that to determine the velocity of a star. And they do other stuff with it, but a lot of this planet searching now, I think they're using that. And I think the Lyman Alpha talk later will go into that. So this is just a couple of pictures. This is diaphy. Okay, this is a 107-inch telescope, and this is diaphy right here on the end of it. It's an imaging instrument. And just a little closer up picture of it. It happens to have some blue on it, but most instruments are black. And so that's another reason I didn't include a lot of instrument pictures, is because they're just black. You can't really see a lot. Okay. This is looking down the bore of the of diaphy. You can see the primary and the secondary up there. And then over on the far end, I guess I really don't have a good angle here. This is a high-res spectrograph for the HET. Actually, it's the old one. And this is, right here is the fiber coming in from the telescope. So the light falls on a fiber and comes in. It goes through some filters. And then right here is a little slit plate that has a bunch of slits in it. And then it goes off. Whoa. There we go. Then it goes off to this mirror and off into the instrument. This is in a meat locker size room. Okay, so it's probably maybe half or a quarter the size of this room. Whereas diaphy is just a little instrument that bolts on the back of the telescope. And so that's the input end over here, and down here is the output end, or the detector end. The light's gone through the instrument, comes through a camera, and falls on the detector right here. That's just another view of the detector, of the body of it. So we'll come back to a couple of those pictures here in a minute. So to design an instrument, an astronomer has an idea of something he wants to do different, or new capabilities, or whatever. And so they talk to people and talk to engineers, and they come up with a set of requirements to be able to satisfy that dream. And they do maybe some preliminary optical and mechanical design so they can get an idea of what it's going to take. But then sooner or later, they're going to have to do some funding. So they submit funding to, proposals. Usually, funding has to be identified, and then we can start on detailed design work. So there are various components to the design. One is the optical design. It's very important. It takes the beam from the telescope, whatever cone angle that thing has, and it couples it up with the detector on the instrument. And along the way, the light is either split into its components or passes through a filter or whatever it does. And part of the optical design, it defines the lenses and the mirrors and their relative positions where they need to be. Okay? And then the mechanical design will then position those optical components where they're supposed to be so that the instrument will work. Some of the components are the mechanical parts of it. A focused image must not move during the observation. All objects in the world have 6 degrees of freedom. And exactly constraining these 6 degrees of freedom will result in a stable and repeatable mount for critical components. Well, I'll just say we love 3-point mounts. I was sitting in the chairs here, and I was going to make a comment about chairs that wobble. They're over-constrained. So, but all these chairs, none of these chairs wobble. So I can't use that. But a door, think of a door. It's got 5 degrees of freedom constrained. And the 6th one is the fact that the door can open and close. Okay. But the other interesting thing about most doors is that they're over-constrained anyway because they have 2 hinges on them, 2 or 3. And a door will really work with just 1 hinge. So that's kind of an example of degrees of freedom. Everything can move in X, Y, and Z, but they can also rotate about the X, Y, and Z axes. And when you're doing a design, you want to exactly constrain those degrees of freedom, but you don't want to over-constrain it, particularly on critical components. So you also have a vacuum. The detectors on instruments live in a vacuum chamber. They help reduce the heat loads and remove moisture and other contaminants in there. The next slide will show that they are cooled with liquid nitrogen or a closed cycle cooler. And so you want to minimize how much heat is in there so that those will hold a lot longer. Typical vacuums are like a billionth of an atmosphere. Very, very low vacuum. And they have to be able to hold that vacuum for many months to be able to be useful. Okay, so here's the thermal stability and isolation. CCDs are typically cooled to around minus 100 degrees C. You need to minimize the heat loads from the surroundings. So you've got the body of your camera, and it's at room temperature, and then you've got your CCD in the middle of it, and it's at a minus 100 degrees. So So this is the CCD, this is the silicon, and then this is the body of it, okay? And here's one, this one's being assembled over here. And you'll notice gold plated. Later on I'll talk about that we gold plate some of these critical parts. But these, and we'll talk about flexures, but these are flexures that mount this. This is cold, this is minus 100 degrees, and this is room temperature, okay? But if this thing moves around, you don't want that guy flopping around, because you remember the mechanical part of it, it has to remain very stable. So these are part of the problems that we have when we're doing designs. So does the instrument move during observation? So like on the HET instrument I showed you, that thing just sits there. It doesn't move. So, you know, you don't care. But the diaphy on the 107-inch telescope, the telescope moves around all night. And so the gravity vector for all the components on that are changing. And so you have to account for that when you're doing your design works. Let's see. So are there moving components? Do you have filters or mirrors that moving in and out? If you do, you've got to have a controller, electronics to move those things around, and then they have to interface with the computers. And then another one is the final alignment capabilities. Generally, when you build a part, you cannot build it accurately enough to align the optics properly in an instrument. So you have to be able to adjust those after you've assembled the instrument to get it lined up properly. And they must remain stable throughout the instrument. Okay, let's see here. That's not what I expected, but all right. So this is I said we have an optical design, and this is what comes out. One of them is the rays. Whoops, I just love this. Okay, so there are the rays, and here's another example of it. So this is the HRS right here, and this is the old HRS. We're building a new one, but this point right here is that slit right back here, and this little fold right here is that mirror right there, and you can't see it very well. There's a collimator. You see how the light's diverging, and there's a collimator back here that collimates it, makes it parallel, and then it hits this a shell grating and breaks it up in one direction, and it comes back through here, and it goes through a focus and back over to this collimator, and over here to a grating, which is right there, and then this is a camera, this body right here, and then the detector's down here. So I was going to step through real quick. Another thing you get out are these optical elements, and this is what the mechanical engineer is interested in, because that's where they need to be, okay, once you get the optical design worked out. And so we have CAD software. We use Inventor and SolidWorks in our department, and we use finite element for determining stresses and deflections. So we import the optical layout and the elements into the CAD, and then we design all the mounts around it. Designing for stiffness, we don't have to worry about the material failing, but we also try to minimize thermal losses by having small cross sections. So those are two counter criteria that we try to meet. Flexures act as a spring, so they give us smoother motion than just moving screws around something. It's very stable. Cryogenic components are used to cool the CCD. There's a telescope interface. You got to get it bolted on there somehow, or a fiber feed. And then you need electronics to run everything. And then here, another key component are baffles, and they're used to eliminate light reflections and reduce scattered light. You only want to look at the light from the star you're interested in, not anything else. Like, even the little LEDs on a power strip, or any little warning lights out in the dome, we have to block out. They typically have sharp edges or stair-stepped edges to help minimize reflections, and this is the set of baffles down inside that diaphy instrument we showed you. And this didn't turn out very well, but you can see the knife edges in here in this tube, and the yellow lines were used to lay out to determine where those knife edges need to be. So I was going to step through just a real quick design, okay? So I picked out this element, and since I couldn't get the animations to work, I just put it all on here at once. So you start out with just a rectangle, you extrude it, you say, oh dang, this is where I need the hole for the lens. So you draw a circle, you bore it out, you do the same thing to get a hole all the way through, and then you constrain it. We did an axial constraint and then a planar constraint right here. And there it is. When I told it to assemble, it put that lens right there in that bore. I changed the color because it didn't show up very well. And then this is the actual part. This is the guider. This is the input head for Virus P, which is the prototype to our current virus instrument. And I think that lens, if I remember correctly, is this group over here. So, and this is a flexure. You see it has a thin cross section. And the nice thing about it, see, it's real flexible this way, but not this way. So I did a quick finite element on this, 10 pounds pushing sideways on it. I can't read that, but I think it was about 0.3 inches. Whereas this over here, it's 0.005. So 5/1000ths of an inch compared to 3/10 or 1/3 of an inch over here. So that's what a flexure looks like. We use those a lot. Last two design considerations. Can the parts be actually fabricated? There are, particularly with young engineers, you run into designs where you just can't make the part. You can't get to it. You don't have the tooling or whatever. For some reason, you can't make it. And then, can the instrument be assembled? Sometimes you got sub-assemblies that you put together and you can't get the holes to attach it, and there's just a whole list of things that could go wrong with that. So it's something we're looking at constantly while we're working on it. Okay, what did I do now? Let's see. Oh, some characteristics of our part. I kind of like these. We often make only one or two of something. We never mass produce anything. Okay, so all of our parts are very unique. And while we like to make simple parts from a fabricating point of view, real easy to do. If you make a mistake, it's easy to fix it. But we often make complicated parts like this one to reduce our part count. And this is a mount for a well, I'll think of it in a minute. Prism, there you go. And this thing's about 2 inches tall and 1.5 inches square, but you see there's a flexure down here, a flexure here. There's some features down here that keep you from bending the flexure too far to deform it. Same way right here. So that's a Brian South part. Actually, he's one of our engineers. And sometimes during final dimensions are not determined until we actually assemble the instrument. Okay, so a little bit about fabrication. We have an in-house shop. It's on the top floor of RLM, so it's 14 stories up. We have 3 machinists. We have 2 CNC mills and a CNC lathe. We also have a wire electro discharge machine or a wire EDM machine. I have a slide, next slide will show it, but it uses 10 and 4/1000 diameter electrically charged brass wire to cut material. It has no tool pressure and allows us to make very thin cross sections, and that's what we make a lot of our flexures out of. We like to use our in-house shop for complex parts or for parts that will take some iteration to determine their final size and configuration. We can just go back and forth to the shop until we get it like we want it. And we use outside shops when we're full or when a part size exceeds the capabilities of our machines. So this is the wire EDM machine. We've had it quite a while now, but it's cut these real thin slots in this plate, and here it's cutting out the center hole. But here's a picture of the wire etching away at the metal. It's slow moving, but it makes very accurate, very high precision parts. So during assembly, instruments are assembled here in Austin to check for fit and function. We look for design and assembly issues and make modifications as we need. It's you just never quite get it right the first time, even with the CAD that we have nowadays. We then disassemble the parts and send them out for metal finishing. Metals are typically aluminums, various stainless steels, and copper. We use a lot of plastics too, Delrin and fiberglass and things like that. The aluminum gets anodized black. Stainless steel is usually painted flat black, and as you saw, some parts even get a gold flash to help increase emissivity so that the radiation gets rejected and it doesn't go into the part and heat up the CCD. Then we take the instruments out to mount them on the telescope. Got to get them cabled up. We have to balance the telescopes. Telescopes like the 107 inch have to be balanced for each instrument that's on it because the motors are relatively small for the mass of that they're moving. So you need them well balanced. You characterize the data from known objects, and sometimes we have to make several trips to get it right. We find something wrong, we go back and have to fix it. And let's see. Okay, so this is the keeping it that way part. We have there. I've lost count of how many telescopes are out at the observatory now. I know of at least 4, 5, 6, 7 that I can think of. But the 82 inch is the original one. Mr. McDonald died in 25. Little court battle with the family. They thought he was crazy. But anyway, they started in 33 and it was dedicated in 1939. The 107-inch telescope was built in the late 60s, and one of the early programs there was using a laser mounted in the telescope to bounce off the retroreflectors that the astronauts left on the moon. They now do that over on a special telescope on Mount Folks. We have a good set of drawings for our telescopes for the most part, but often we don't know what the design intent was of the designers. So we have to kind of make it up. That's what I call the forensic engineering. We make it up as we go along, figure out what works. Occasionally instruments need to be repaired, but it's not common if they're well designed. And like I say, see part 1 of my talk and you won't have that problem. But instruments tend to, of course they're not around always as long as telescopes, but my second day on the job I drove the Casa shell out, or went with a group, drove the Casa shell out to the 82 inch, and it's still being used out there, so they do stick around. Let's see. So, a couple of just example type issues. So this is the 107 inch telescope. This dome is 220 tons, okay, 440,000 pounds. It's a honker. It has 36 support rollers, 2 of which are drive rollers, kind of similar to a railroad track configuration. And a couple of years ago, one of the drive roller assemblies, they have 2.5 inch studs in them. One of the studs broke. So let's see here. So this is where the drive roller lives. This is the interface between the dome and the building, okay? And so this is the stud that broke right there, okay? And I guess my picture's over the stud there, so you can't see it. Sorry about that. But this is also the mount that is part of it in here. It supports, this is the drive motor and the gearbox and the drive gears and stuff, and all that stuff's bolted to this guy. And you can see there's an example of where it was torn. The metal's just ripped apart. You can see some, if you could really see this picture, you'd see that welded on this over the years and stuff. And there's the drawings, kind of drawings we have to work with to figure it out. And then we cleaned up the mount, and we made some new studs. The studs actually go up into this guide roller here, and so they have a lot of features up in here. So we built a few of those in our shop, and we got back in service. The telescope was able to operate for several months with just one drive roller, so it wasn't critical, but we did have to kind of stay after it. Let's see. Oh yeah, so here's one more. In addition to so this is the dome wheel. We have 36 of those. And these are guide rollers, and then the rails running right here in the middle. And we've found that some of these guide rollers are starting to fail. These are now 50 years old. And the hardness, this should be straight all the way down. And you can see it's worn up in here, and now the hardness layer is cracked and it's starting to chip away. So we're in the process of working to get those fixed. We bought some new guide rollers, and we'll probably start replacing those next month. Okay, we're coming to the end, so don't worry. I see we're about out of time here. So this is my most useful project in 25 years, okay? This is a mirror jack for the HET mirrors. You know, the HET is made up of 91 hex-shaped segments, and before this came along, there are 3 30-millimeter studs, and somebody would have to sit there and crank those things about 12 to 15 inches up so they could get the mirror out. And so there's the jack. It sits down in the crotch of the support. You know, we catted it up. I tested it in my office with about 300, these weigh 300 pounds. And you can see I had it tied off to the door hinge and my table and everything else. And I had about, there's 200 pounds, but I had another 100 pounds on it. And so I was testing it out. And unfortunately, I couldn't find a slide with a mirror on it, but we used weights from a dumbbell set. And you can see it in the truss here on the mirror, and we were able to extract it. And they use that now. Instead of doing 2 mirrors a day with a lot of hard work, they can do 3 or 4 mirrors a day on the HET. And it just uses a cordless drill now to drive it in and out. So I feel like that's one of the best projects I've had and most useful, helping mankind. So anyway, that's all I got. Sorry it took so long.
Thank you. No, that's fine. We have some time for some questions. Right there, sir.
Do you ever use 3D printing for fabrication? We don't use, he asked if we ever use 3D printing for fabrication. I don't. I have a 3D printer. I do it for prototyping, for testing stuff out. The guys down the hall that are working on the virus project, they've done some 3D parts for fan covers and things like that. They've got 80 or so controllers that they need to fans on, and so they've been doing some of those with 3D printing. But it's all plastic and stuff. Yes? He asked if we ever have stuff coated and it comes back from the coater and the coating's too thick and things don't go together. We haven't necessarily had that problem. We mask off sometimes areas of where it's critical, where thicknesses are critical. We mask it off so it doesn't get coated. Or if we need electrical conductivity, because anodizing is an insulator. But you can tell an instrument that's been reworked because it's got all these holes and stuff in it that where they cut through the had to cut through the anodizing. So we just take a magic marker and fill it up.
With the hat?
How has your job changed in the past couple of years, like software?
That's fun. He asked how my job has changed in the past 20, 25 years. It is different. You know, when I started, when I started, we were using AutoCAD, and it was 2D flat file type of stuff. We still had drafting tables around, but we didn't use them that much. And you know, you do a drawing here, you do a drawing here, and you hope the holes line up, but you can make a mistake between the two. Nowadays, with 3D CAD, I can make 2 parts. And if I use the holes to constrain the part, I can tell if the holes are lined up correctly and things like that. So our mistakes have gone way down with the modern CAD. And with the finite element, it lets us better design things without over-designing them.
Okay, great. Thank you, Gordon. Let's give him another round of applause.